Welcome everybody to the third video lecture in discrete mathematics. In this video lecture, I will be talking about propositional and predicate logic. This will help us set up the mathematical foundation using which we will be writing mathematically sound proofs. To start with, let us consider any logical statement. You can think of a theorem, for example. It comprises of two parts. First part is a premise or a set of assumptions, and the second part is a deduction. The premise or the set of assumptions can be composed of multiple smaller statements, each of which individually can be true or false, or in other words, each of the smaller statements can either be satisfied or not. And these smaller statements are connected using connectives like and, or. Similarly, the deduction can also be composed of multiple statements connected using connectives. For example, let's consider this following statement. When it's cloudy, it rains. Today it's cloudy, so it would rain. It is a statement, a logical statement. It has some set of assumptions and a deduction. Now, what are the set of assumptions? In this statement, this sentence, when it is cloudy, it rains, and the sentence, today it's cloudy, are both part of the assumption. And what's the deduction? The deduction is it would rain today. As you can see, the assumption comprises of two statements, and ideally one should think of it as when it is cloudy it rains and today it's cloudy. That is the assumption. And the deduction is it would rain today. So we see that the assumption is composed of two statements and connected by the connective and. Now, when it is cloudy, it rains. This can be true or false. Similarly, today it's cloudy can be true or false. So thus each of the individual statements can either be true or false. Similarly, consider another example. Every city in India has horrible traffic. Chennai is an Indian city, so Chennai has horrible traffic. Now, what is the deduction here? The deduction is Chennai has horrible traffic. What are the assumptions, or what is the assumption? The assumption is every city in India has horrible traffic and Chennai is an Indian city. So, formally speaking, in propositional logic and predicate logic, we say that every statement or proposition is either true or false. These statements can be composed of other smaller statements, and they can be connected using 5 different kinds of connectives: and, or, not, implies, and if and only if. A statement can have unspecified term called variables. Each variable has to be quantified properly. Let's go back to the examples that we were seeing just some time ago. So in the first example, as you can see, there are no variables. It says that when it's cloudy, it rains, and today it's cloudy implies it would rain today. Thus, we had 3 different statements, and they are connected by the connective and implies. On the other hand, in the second example, there is this statement every city. Now I have not told what city or which city and so on. So this statement every city in India has horrible traffic is a statement where the city is a variable. And this term every city is kind of used to quantify the variable. So we have every city in India has horrible traffic is a statement having a variable which is quantified using the quantifier every. And we have the whole sentence as every city in India has horrible traffic and Chennai is an Indian city implies Chennai has horrible traffic. You should understand that when we write something in English, we need not use the exactly same words as the connectives. For example, and, or, implies, if and only, if and not. We might use something else, some other synonym. So to understand an English sentence, we have to understand what is the inner meaning of that. So, and that and can be replaced by a full stop or something like that, as you can see in these two examples. Now, the connectives of and, or, not, implies, and if and only if satisfy some rules. And these rules are guided by our usual understanding of connectives. By the way, the connective and in mathematical term is represented using this particular notation, or is represented using the inverted V, not in this example with this notation, implies with this implication mark, and if and only if with the double implication mark in either direction. Now, the connectives and, or, implies, and if and only if takes two statements, each of which are either true or false, combines them to produce a single statement that is either true or false depending on the input statement. So in other words, these connectives are a function from true comma false whole square to true comma false. Connective not takes a single function and produces a new function. So the not is a function from the set true comma false to the function true comma false. Let's see some of the rules that are used for and, or, implies, and if and only if. So here is the truth table. You can go over the truth table and you understand what does it mean by each of the statement. Now this is the way we should read it. So if P and Q are the two statements and we are saying statement like P and Q. So if P is false as well as Q is false, then P and Q as a statement is false. This is kind of natural, like when we say that this happens and this happens, and if any one of them doesn't happen, it means that the whole thing as a whole also doesn't happen. So false and false gives false. Similarly, false and true gives true. True and false gives false. And the last one is true and true gives true. That means only when both P and Q are both satisfied, or they are both true statements, only then the combined function of P and Q is also true. Similarly for or, for example, say if I say that I will either give you an A grade or I will give you an B grade. Now this says that as long as I do either of those two objects, the whole sentence is true. So in other words, as long as one of P and Q is true, I get true. Whereas if both of them are false, then the function evaluates to false. For the connective NOT, it just flips the function. It just adds a negation to the statement, and just a false statement becomes a true statement and a true statement becomes a false statement. Now let's consider this interesting function of implies. When can we say P implies Q is a right statement? So when the mathematicians and the logicians were setting up the mathematical foundation, they were divided as to how to define this particular function implies. So one thing that they decided is that a true statement always proves the true statement. Hence, if P is true and Q is true, then the function P implies Q is also a true statement. At the same time, P cannot imply the false statement. That's the other way of saying it. So if P is true and Q is false, then the whole statement has to be evaluated to false. Here is one slightly more complicated thing, that a false statement can prove any statement. So in other words, if P is a false statement, from that I can imply anything, which means false implies true is also true, as well as false implies false is also false. There was a lot of debate on this, and one beautiful story that goes along is that when the mathematician G.H. Hardy was asked to comment on this statement, or was asked to comment on this particular rule for implies, he was asked to prove that, can you prove the following statement? If 2 plus 2 equals to 5, then you are Pope. Now clearly 2 plus 2 equals to 5 is false, and you are Pope is also a false statement. Now can a false statement imply any false statement? For example here. And G.H. Hardy did give a proof, and here is a very cute proof of that. It says that 2 plus 2 equals to 5. Now everybody knows 2 plus 2 equals to 4. That means 5 equals to 4. If you subtract 3 from both sides, you get 2 equals to 1. So 2 person equals to 1 person. Therefore you and Pope are 1 person. Hence you are Pope. This is a very cute proof or very cute example that shows that if you assume something is false, in this case 2 plus 2 equals to 5, then you can prove any ridiculous statement on earth. For example, you are Pope. So in other words, for the case of implies, it is accepted that a false statement implies any statement. Thus, the truth table of the implies function has false implies false is true, false implies true is true, true implies false is false, and true implies true is true. Similarly, we have the other thing of if and only if, and I leave you guys to convince yourselves that this particular truth table also makes sense. Now there are two quantifiers also that are there. As I told you, every variable has to be quantified, and these quantifiers are for all and there exist. And you write statement like this. So this says that there exists x such that P of x is true. This is how you should read this statement. Similarly, this one says that for all x, the statement P of x is true. If you recall the example we had used, there was this example of every city in India has horrible traffic. So in that respect, X is the city, every means for all, so for all city, and the statement was the city has horrible traffic. So it should read as for all city in India has horrible traffic. Now, it's a nice important fact that using these 5 connectives and the 2 quantifiers, they are existent for all, one can write any logical statement. So these are called kind of universal set of notations using which any logical statement can be solved or written. Let's see some example. Let us take a normal logical statement to a mathematical logical statement. For example, consider this particular para. This says that if you did not know the material earlier and you don't study hard, then you will not get an A in this course. Therefore, if you get an A in this course, then you knew this material earlier or you studied hard. Now, I would like to check the logical validity of this statement. First of all, we should understand that this statement as a whole is either true or false. And this statement is true or the statement is valid if for any condition satisfying the premise or assumptions, the statement holds true. So in this particular case, we have to understand what are the premises, what are the deductions, and what are the connectives. So if you want to ask, is the above statement true or false, let's try to convert it to a mathematical statement. To start it, as you have seen, a statement can be formed using other statements. For example, here, you did not know the material earlier is a smaller statement. This statement can either be true or false. Either you knew the material earlier or you did not know the material earlier. In any case, this is a statement that can be true or false. Similarly, you don't study hard is a statement that can be true or false. There are other statements here. I let you guys to look around inside the para and identify the set of statements. Now these statements are connected using connectives like and, or, not, implies, and if and only if. As I told you earlier, not necessarily this exact set of words of and, or, not, implies, if and only if will be used. One can use other synonyms of it. For example, in this case, and, then, therefore has been used. So then and therefore are actually synonyms of implies. Now that we have understood what are the connectives and possibly what are the statements, let's try to convert this statement or this para, this English para, into a mathematical logic statement. To start with, let's take the first statement that is there, and that is you did not know the material earlier. Now this is a statement. I don't know how to break this statement into smaller statements, and hence I call this one a variable. Let's call this P. What is the next statement that is there? It is you don't study hard. Let's call this variable Q. What is the third one? Third one is you will not get an A in this course. Let's call this one a new variable R. Now what is the next one? Here is another statement. You knew this material earlier. Now, what is this statement? So, what is this statement? You knew this material earlier. Note that if P indicates the variable is the variable indicating you did not know the material earlier, then you knew this material earlier is nothing but not of P. Thus, after we have put variables for these three statements, we can have you knew this material earlier as not P. Similarly, you studied hard is nothing but not Q. And you get an A grade in this course is nothing but not R. Now, using this set of variables, how can we represent this statement? Let's see. You can check for yourself that we can write it in this following fashion. And the reason we can write it in the following fashion is that we can read this sentence from left to right and you will see that this para coming up completely. For example, since P is you did not know the material earlier and so on, I will just replace the P, Q and R with the English sentence. You did not know the material earlier and you don't study hard implies you will not get an A in this course. Thus, or therefore, you get an A in this course implies you knew the material earlier and you studied hard. So this English sentence has been converted into a mathematical logic statement. Thus, the sentence is logically correct if in whatever ways I put P, Q and R as true or false, this following equation or statement must evaluate to true. So to check if an expression is correct or consistent, we will try all possible values of the input and see if it always evaluates to true. One way of doing it is to write down the truth table of the equation exactly. That means for all the possible choices of P, Q and R set to true and false, so there are 8 of them, does the function f, which is this function on top, evaluate to true? And the way to do it is to do the whole truth table. Now, as you can see that the evaluating the truth table is a slightly tedious job, and we break it down to smaller parts. Namely, let's say f is S implies T. That means this is S and this is T. Now, to evaluate S, I have to have P and Q implies R. So I first has to evaluate what is P and Q, and then I have to go for P and Q imply R. So here is the first few steps. So P and Q is following the truth table of AND. So that means if both of them are false, it is false. If one of them is false, it's also false. And only when both P and Q are true, it evaluates true. Now, if this is G implies R, when is that true? Now, for example, say false implies false is true, because as we have discussed, false statement implies any statement. So similarly, you can do it for all of them. False implies true is true, false implies false is true, and so on and so forth. True implies true is true, true implies false is false, and so on. Similarly, we can do the not of P and not of Q and not of R, which is using the truth table of not. And then I can evaluate what the value of T is by doing the same thing. First of all, doing it as not of P and not of Q, and then not of R implies not of P and not of Q. And once we have that, we have this S and we have this T, and thus S implies T. Let's see, true implies true, right? True implies true, correct? True implies false, and that is not true, that is false. So in fact, when you write down this whole equation, you realize that the function f evaluates to false at two cases and true in the rest. So since the expression does not evaluate to true always, so the expression is not correct. This is possibly something that you could have understood by looking at this sentence as an English sentence earlier also. But here is a mathematical way of proving that this English sentence is wrong. So to recollect what we have done till now, we have set up the basic for the propositional logic, where every statement is either true or false. The statements are connected using 5 connectives, that is and, or, not, implies, and if and only if. And a statement can have some unspecified term, but that has to be quantified using one of these two quantifiers, for all or there exist. We have also seen that any logical sentence, particularly any logical English sentence or mathematical sentence, can be converted to a logic statement, and that can be used to check whether the logical sentence is consistent or not. And the way of checking it is by ensuring that for any input of true and false to the smaller statements, does the whole statement evaluate to true? So does the whole statement evaluate to true at all the time? Here are a few problems on propositional logic. This brings us to the end of the video lecture. This was an introduction to propositional logic and predicate logic. Next week we will see how this particular framework helps us to understand proof techniques. You should try to solve these problems yourself. I will discuss these problems in the video lecture where I do a lot of problem solving. Thank you.